Hello, everyone, and welcome to another online Stat 4243 lecture. In today's lecture, we're going to pick up where we left off at the end of the last video lecture. And so in the last lecture, we sort of finished talking about Monte Carlo integration, and then I started to introduce this idea of parametric versus non-parametric inference or estimation in statistics. And sort of the key idea that we were thinking about is that with parametric inference or parametric estimation, which is sort of what we're most used to dealing with in our statistics courses, we're making very explicit assumptions about, say, the distribution of the data that we've gone and collected. And this works out quite well, right? So there's a lot of benefits to doing this parametric estimation. However, we run into troubles when we are sort of in a situation that we can't be sure that the assumptions that we're making are correct. And a lot of the techniques, if the assumptions you're making are incorrect, sort of start to break apart, right? And so we introduced this idea of non-parametric estimators or non-parametric inference, where the idea was, let's try to come up with statistical techniques that don't make explicit assumptions about the distribution of the data, and as a result, they'll sort of work for any problem, right? And this was sort of this grand idea. Now, there are going to be some drawbacks to this, and it's sort of worth investigating what those are. In particular, if you have non-parametric techniques, they're typically going to require a lot more data to be effective than a parametric technique would, right? So this is going to be sort of one of the major downfalls here. Now, before we get sort of into talking about parametric and non-parametric estimators a little bit more, I think I should spend some time trying to address why this is relevant for where we're at in the course so far. And so the motivation that I'll sort of put forth for this topic is that if you think about what we were doing with Monte Carlo techniques, right, we're essentially using the pseudo-random generated variates in order to either, say, test statistical methodology, to estimate particular traits from a distribution, to see how estimators perform, or to solve integrals in the case of Monte Carlo integration, right? And in each one of these cases, essentially what we did was we determined some underlying distribution, and then we generated data from that underlying distribution, and we used that as the data that was sort of relevant to us, right? And so if you wanted to see what's the coverage probability for this confidence interval, right, we generated data from some distribution. And so in some sense, Monte Carlo techniques are a form of parametric inference, right? And so what you might think that you could do, for instance, is if you were pretty sure that a data set that you had generated or that you had observed was from a normal distribution, say, you could go and estimate the mean and you could estimate the variance, right? And then essentially what you're saying is my data is coming from this specific normal distribution, right? Maybe a normal with, a mean of 10 and a variance of 15, right? Whatever the case happens to be. We could then use Monte Carlo techniques to randomly sample pseudo-random variables from that normal 10-15 distribution, right? And in doing so, essentially what we're saying is that if that distribution is correct or is approximately correct, then the data that we're generating from this Monte Carlo procedure are going to look like the data that you've actually generated or observed in your sample. And so if you wanted to, say, test out how does an estimator perform, then you could do it through this procedure. So maybe I'll open up sort of the whiteboard here and sort of write down what we're thinking about, right? So if you observe, say, x1, x2, up to xn, right? And let's say you are willing to assume that the xi are IID from some normal distribution with a mean and a variance, sigma, mean mu, sigma squared variance, right? So then what we could do is we could say, 1, estimate mu as x bar, for instance. 2, estimate sigma squared as, say, s squared, right, the sample variance estimator. And then what we're saying is that, therefore, the xi are going to be approximately a normal distribution with x bar s squared, right? And so then let's say that we have some estimator, right? So we have theta hat, right? And it's going to estimate something from our distribution. And let's say we wanted to know, for instance, what is the variance? Right? If you are willing to make this assumption that we've sort of set up here, one thing that you could do is you could say, well, we can estimate the variance by actually repeatedly computing this estimator, right? So you could say, to estimate, step one would be generate, say, x11, x12, and so forth, up to x1n, which would be IID from this normal x bar s squared, right? So generate, using Monte Carlo techniques, a sample from this distribution, and then compute theta hat 1 on that generated sample, and then repeat, say, m times, right? So this is going to give us, right here, theta hat 1, theta hat 2, up to theta hat m. Right, so what we think about what we're doing is we've used our original sample to figure out what is the distribution of this population, or what's the approximate distribution of this population. And then we use Monte Carlo techniques to repeatedly sample from that approximate distribution so that we generate this whole sequence of estimators that are computed on Monte Carlo data. And then what we could say is that the variance of theta hat should be approximately equal to the sample variance of these different estimators, right? So that would be something like 1 over m minus 1, the sum from I equals 1 to m of, say, theta hat I minus, and then I'll write theta hat I, or just theta hat bar, for instance, squared, right? So the sample variance of this. And if you get the distribution correct, this result's going to hold sort of through all of the arguments we were making about Monte Carlo estimation. And so it's really sort of useful to think about Monte Carlo as though it's a parametric technique in some sense, right? So in some sense, we're making assumptions about the distribution of the data that we have. And then once you have those assumptions, we know how to generate from any particular distribution, right? But this technique right here, it's not going to work if you don't know what the distribution of the data are, right? Because how are you going to calculate the variance of your estimator when applied to a real-world data set if you don't know sort of where that data is actually coming from? And so the goal with our discussion of non-parametric techniques is to get us to a point where we can take that same process that we just covered, where you would be able to, say, estimate the variance of an estimator using Monte Carlo, and be able to do this even when we're not willing to make specific assumptions about the distribution of the underlying data, right? And because we're not willing to make specific assumptions about the distribution of the underlying data, this is going to be non-parametric, right? And so in that way, what we're hoping to do is sort of build up a non-parametric version of the Monte Carlo techniques. And we're going to end up calling this the bootstrap. So if you've seen that before, the bootstrap is sort of a non-parametric version of Monte Carlo. But in order to get to explaining the bootstrap, I think it's important for us to at least take a slight detour into talking a little bit more broadly about non-parametric techniques and non-parametric inference, right? So just to pull up the course notes here for a moment to sort of guide us through where we're at. In the last lecture, we sort of introduced parametric inference, right? And I sort of indicated that this was the type of inference that you're most used to sort of thinking about, right? And the idea is that sort of to make it as applicable to the real world as we can, typically we're not going to know what a distribution is. It's often not even going to follow some nice closed form distribution at all. So we introduced this idea of non-parametric techniques. And in the lecture last time, I sort of motivated that we at least have a sense of some non-parametric estimators, right? So if you think about the sample mean sort of at no point indicates that you know what the distribution is, right? And so because of that, we can view the sample mean as a non-parametric estimator to the expected value of a distribution, so long as that distribution actually has an expected value, right? And so we sort of set up this integral, right? We talked about this sort of change in format from what you're used to looking at with integrals, right? Because maybe we don't even have a density, but we can still sort of think about it as a functional from the CDF to the real numbers, right? And so then we talked about how that's a consistent estimator. We did the same thing with the linear regression estimators, right? And so you can estimate beta 0 and beta, the slopes, as well, without actually making an assumption about the error distribution here. And sometimes we'll assume those errors are going to be normally distributed because that helps us with inference or with sort of prediction intervals or that kind of thing. But you don't actually need that in order for the estimation of those slope parameters to be valid, right? And so we actually have seen some non-parametric techniques already. And it turns out that, coming up with non-parametric techniques can be sort of a challenge, right? It's not always easy to know how you can non-parametrically estimate something. But just like we have sort of the maximum likelihood estimation or method of moments estimation to come up with parametric estimators, sort of as a general rule, we're going to have sort of a general purpose way of coming up with non-parametric techniques. And it's not always going to work, and it's not always going to be sort of the best thing for us to do. However, it sort of gives us a general purpose idea to try to come up with a non-parametric technique. And so it's a really good place to start. And so what we'll do in today's lecture is talk about that. It's something known as the plug-in principle or the plug-in technique. We can form plug-in estimators through it. And in order to talk about that, it's going to require us to explore the empirical CDF a little bit more. And I know we touched on this when we were introducing sort of our background mathematical statistics, but we'll talk a little bit more in depth about that today. And then sort of from there, we'll have a basis of how do we think about non-parametric inference, and we can start using that to jump off and explore the bootstrap and sort of these non-parametric extensions to Monte Carlo estimation techniques, right? So with that, we can open up our whiteboard here again, and we can start talking about the empirical cumulative distribution function. So sort of the setup that we're thinking about throughout this whole procedure is that we're going to be assuming that we have some sample, we'll say x1 through xn, and the only thing for right now that we're going to assume is that this is coming from some distribution with a CDF given by f, right? We can always say that a random variable is going to have a CDF, right? And so it's sort of uniquely defined by its CDF. And so this is sort of a valid place for us to begin. And the idea is that, if you were willing to assume some distribution, right, then this CDF in this sort of parametric case, right, if you assume some distribution, then in that case, f is going to be governed by some parameter theta. Right, and so what we're thinking about here is, for instance, if you take the normal CDF, right, so if normal, then what you need to do is you take theta is equal to the mean and the variance, right? And the idea is that in this case, once you know the mean and the variance, then you know everything about that distribution, right? Similarly, if you were to take it to be the exponential, then theta is just going to equal the rate parameter, which is lambda, right? And so again, in these cases, all we have to do is estimate the parameters, and then we know the distribution. But if you're not going to assume some particular distribution here, then there's not going to be a single parameter that sort of indexes this function that we care about, right? And so instead of trying to estimate the parameters, what we want to do is estimate the function itself. Right? So we don't want to say, well, to get to our CDF, we need our mean and our variance. Instead, we want to say, let's estimate a function that's going to approximate our CDF, right? And so how might we think about going to do this? Well, it's worth sort of thinking about the fact that if you take, say, f of x, right, by definition, this is the defining relationship here, this is going to be the probability that x is less than or equal to this value x, right? This is true by definition. And so how might we think about trying to estimate this? And sort of, I think the natural way is if you think about having a bunch of data, and let's say that we order all of our points here, right? So we take x1, x2, and so forth, up to xn, right? These are what we would call the order statistics. And we call them the order statistics when we've placed them in order, and we typically write them with this sort of subscript bracket rather than just sort of x1 through xn, right? But if you take them in order, then sort of a question you could ask is, where does x fall, right? Where can we put x into here? And then you count the proportion of values that are less than here, right? So then the proportion here. And so maybe to make this concrete, right? Let's suppose that we observe the values, I don't know, 1, 1, 2, 5, 7, 8, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll just take a 10th to make our math easy. Right, so let's say that these are the order statistics of the random variables that we've actually observed here, right? And then if we wanted to estimate, say, I don't know, f of 6, right? Which is the probability that x is less than or equal to 6, right? If we assume that the data that we've observed are going to be somehow representative from the true distribution, which, depending on how we've sampled it, they should be, well, then what we note is that 6 is going to fall right in here, right? And so if we look at this, then we've observed 1, 2, 3, 4 values that are less than 6, and then we would have the other 6 values being larger than 6, and so then this should sort of be approximately equal to 4 out of 10, right? Because 4 out of 10 of the values are less than or equal to 6, right? And this sort of makes sense, and you could think that, well, if we sort of take a larger and larger sample size, then of course, eventually this is going to give us the correct sort of distribution here. And this sort of intuitive idea is the basis for the CDF, right? Or the empirical CDF. So how do we get the empirical CDF? Well, to get the empirical CDF, we first define our indicator function, right? So let, say, the indicator function here, xi less than or equal to x equal, say, 1 if xi is less than or equal to x and 0 otherwise, right? So it's a function that's going to map to 1 if this is true, and it's going to be 0 otherwise, okay? And so once we've defined this, well, then what we can do is we can say the empirical CDF, which we denote as f hat with a sub n, right? And the sub n is to emphasize the fact that this is going to depend on the sample size that we've actually observed. It's going to be a function, right? So we take in a parameter value x here. And what we're going to do is we're going to write this as the average of the summation from I equals 1 to n of the indicator function of our sample less than or equal to the parameter value here, right? And so what we're doing here is we're counting up how much of our sample with this summation, right? This is going to give us the number less than or equal to x, right? And then we divide by the total number to give us the proportion, right? So this is exactly what we were doing up here. It's just sort of written out in this notation. And one of the nice things about writing it out in this notation is that we can see that the empirical CDF here is going to be a sample average, right? So for every single value, so for any fixed x, f hat of n is a sample average, right? And why do we like the fact that it's a sample average? Well, what we know is that sample averages are going to converge based on the laws of large numbers to the expected value of that sample, right? So what we can say is that therefore f hat n of x is going to converge, and we can say it's going to converge almost surely, or we could say it's going to converge in probability, depending on whether you're referencing the strong or the weak laws here, to the expected value of our indicator function xi less than or equal to x, right? And if you think about what this expected value is, right, well, we could actually write this out as an integral here, right? So the integral here is going to be the integral over the real numbers of this expectation. So I will take a different integration variable. I'll integrate over t, right? Just because we have this x here. So it's going to be the function t less than or equal to x. And then we can use sort of this notation that we've been talking about here, right? Because we're integrating with respect to this CDF. Now, if you think about what's happening with this function right here, right? If we graph this out, well, this function is going to be at a value of 1 up until whatever value we have as x, and then it's going to be 0 for the rest of time, right? And so we can rewrite this as the integral from negative infinity to x, and then this whole function is sort of taken care of, and so then we can just write that as df of t. And this is, by definition, the CDF, right? So this is just equal to f of x. I'm going to make sure that that's a lowercase x there, right? So in this sense, we have this empirical CDF is going to be converging, at least point-wise, for every single value of x to the CDF at that same point. Now, the thing that I'll point out here is that we could have gotten to the empirical CDF through this sort of defining relationship, right? Because if we look at what this is right here, right? So we take this and we say, take theta of f to be equal to the integral over the real numbers of this indicator value that t is less than or equal to x, df of t, right? Then if we take theta of sort of f hat n, right? Well, then this is going to be the integral here over this function, and we'll take it with respect to f hat of n. And whenever we're sort of integrating with respect to these discrete valued CDFs, right, and sort of our empirical CDF here is this discrete valued CDF, then what it actually becomes is the integral becomes a summation, right? So we talked about this when we were introducing discrete versus continuous, is that we sort of write down everything as though they're integrals, but when we have discrete valued things, then they're actually sort of summations, right? And so what this actually is here is this is going to be the summation over sort of, we could still sum over the real values of the indicator that t is less than or equal to x, but the only values that are actually going to have sort of the positive probability here are going to be the values from t, I guess we could rewrite this based on sort of the notation we were using, xi 1 to n indicator of xi less than or equal to x here. And sorry, the important thing that we have here is that because the density or the mass function here is 1 over n, I should have included my 1 over n here, right? So this is sort of the moving from discrete to continuous or continuous back to discrete. We always can just write integrals as summations or vice versa, right? And so the idea that I'm sort of getting at here is that we could have viewed this as sort of a non-parametric estimator in essentially exactly the same way as we did with the sample mean, right? And so if we open back up our slides here, you can see that our sample mean we define as sort of this integral, right? And then, or sorry, the population mean we define as this integral here. And then the sample mean becomes 1 over n, the sum over these values. And so we're essentially doing the same thing here, but you could come up with the value for the empirical CDF in a little bit more intuitive of a way, I guess, than just doing that. But that connection is going to be sort of important, right? And so we can take our empirical CDF to be defined right here, and it's going to be valid sort of no matter what, right? And so we can take a look quickly at the empirical CDF in R, right? And so we have sort of this code here. I'll zoom in a little bit to make sure that it's all legible, but we have sort of some code. The important function is going to be this ECDF call right here, right? And so what we can do is we can, just generate some data. So we'll set our seed. We're going to take one sample. It's going to be just a normal. And then we're going to take this other sample here. And it's going to be this like weird distribution where we take a normal, we multiply it by some binomial, and then we add on a Poisson multiplied by some exponential, right? I'm sure you could work out what the distribution of this is going to be sort of using transformation techniques and the like, but that's going to be kind of annoying to do, right? And so what if this is what our data actually ended up sort of looking like, the sort of important thing to note is that the ECDF does not care whether we have nice normal data or whether we have this sort of strange mixture distribution. And so then we'll compute the ECDF. All you have to do is you call the ECDF function and you pass in the data that you want here. And then we can easily sort of just plot these, right? And so we'll plot the normal, and then onto the normal plot, I'm also adding the actual normal CDF, right? So that we can get a sense of what it looks like. And then we can plot out this strange mixture CDF here, right? And so we can see that we sort of can estimate all of these values here, right? And you can see these sort of stepwise function right here, that's our estimated value. And the actual curve is sort of what's going on here. So we can see we're at least roughly following the same shape, right? Over here, we can see that we get sort of this more aggressive looking CDF that we're estimating from. I haven't included the actual CDF here because, again, that's going to be sort of an annoying thing to work out. So it's worth popping back over here and just talking about sort of this shape that we're going to always expect to get out of the ECDF, right? So if you think about having observed values in order, say x1, x2, up to xn, right? And then you think about actually treating the ECDF as a function of f, or of x, right? So f hat n of x, right? We can think about what these values are actually going to be, right? So note that we're going to have the proportion of values that are smaller than the value of x that we plug in. And so if we take anything that is less than our smallest value, the proportion of values that we observe down there is always going to be 0, right? So we're going to take 0 for all x less than x1, right? And then what we'll find is that we get a value of 1 over n for all values of x1 less than or equal to x less than x2. Because if you fall between your smallest value and your second smallest value, then we're going to be in this situation where 1 out of the n values are right there, right? Then we'll have 2 out of the n proportion if you fall between x2 and x3, right? And you can sort of continue this pattern here, right? Where we're ultimately going to have a sort of I out of n if you're falling between xi and xi plus 1, until ultimately, sort of make sure to write this in nicely here, until you get to a value of 1 if you are sort of greater than or equal to x, or the maximum value xn, right? So in this case, we can sort of actually think about writing this out sort of explicitly. But if we think about this sort of then emerging as an actual function that we can draw out here, right? And if I place in just some of these values, x1, x2, x3, and so forth, right? Think about this continuing. Then what we're always going to have is this sort of staircase pattern, right? Where we're going to start out at 0, right up until we get to x1. And then immediately we're going to jump up to 1 over n, and we're going to stay constant there. And then we're going to jump up to 2 over n, and we're going to stay constant there, and so forth, right? And so in this case, we're going to always get this sort of staircase pattern, right? And with this staircase pattern, this is sort of the characteristic pattern of any discrete CDF, right? And so in a sense here, if you're thinking about sort of a discrete random variable here, then it sort of makes sense that we're getting out this sort of stepwise pattern, right? And so just to sort of plot this, we're 1 over n here, we're 2 over n here, and so forth. You continue up and up until you get to the value of 1. And so importantly, the thing to note about this is that f hat n of x is a valid CDF, right? So not only is it going to be sort of a good estimate, right, in that sense that we saw with the converging pointwise, but it's also going to be a valid CDF. And what's it going to be the CDF for? Well, it's going to be the CDF for the discrete distribution which is equally likely to take x1, x2, up to xn. Right, so if we define a discrete random variable which has an equal probability of taking on any of the values that we've observed, then f hat n is exactly the CDF for that, right? So it's essentially a discrete uniform probability distribution that assigns 1 over n mass to each of the options that we've actually looked at. And because it's this valid CDF, what we can sort of think about is it's defining this valid distribution. And so we can start to work with that distribution directly, right? And in particular, we're going to be calling this the empirical distribution. Right, so it's going to be called the empirical distribution, and the empirical CDF is the CDF of the empirical distribution. Right, so there's sort of two ways that we can go about thinking about the ECDF. On one hand, we can think about it as an estimate of the true population CDF, and it's a nonparametric estimate, right? So it's going to work sort of no matter which data set we're working with, what population distribution we're working with. It's also going to be the valid CDF of the empirical distribution, right? So if you had a discrete distribution that took on each of these values with equal probability, this is going to be the CDF for it, right? And so both of these formulations are going to be important for us to really understand the properties of the ECDF. Now, there are some other important features of the ECDF that are worth at least highlighting. We won't actually go about sort of proving these or demonstrating them in detail. They sort of require a little bit more machinery than I think is worth sort of going through in this class, but they are important results nonetheless, right? To at least justify why we're thinking about this distribution. And so the first is that we are going to have convergence in distribution of the ECDF at any given point, right? So we can essentially use the central limit theorem because, again, we have this sample average. And so if we think about sort of one way that we can formulate the central limit theorem, what we can say is that the square root of n times by f hat n of x minus f of x, right? We know from our central limit theorem that this is going to generally converge in distribution to the normal distribution, right? So it's going to converge in distribution to a normal, and it's going to be a normal with 0 mean, and the variance is actually going to be given by the Bernoulli variance here. So that's f of x, 1 minus f of x, right? And so that's sort of an intriguing result that we have there. And this is going to be useful. For instance, we can use this to formulate confidence intervals around our ECDF, right? So that's sort of a helpful place that we can sort of apply this technique to. Now, both the central limit theorem and the laws of large numbers, when applied to the empirical CDF, give us results that rely on pointwise convergence, right? So this is saying for each value of x, this is going to be true. there are actually a lot stronger results that we can get from this. And so I'll just state the next sort of result. And this result gives rise to many other results. And it's a lot more powerful, even if at sort of the outset, it doesn't look like it's a whole lot different. So one way that you can sort of write this is we can say that the norm here, and I'll explain exactly what this notation means in a second, the infinity norm of the empirical CDF minus the actual CDF converges almost surely to 0. Right, and so what am I actually saying here? Well, this right here we can take to be the supremum from X of the difference between the empirical CDF and the actual CDF, right? And so remember that the supremum is an upper bound on the difference between these things. So it's sort of like saying the maximum value here. And so the maximum difference between these 2 points for all of the possible values is going to converge almost surely to 0. Now, this is sort of a much more powerful statement than the statement regarding pointwise convergence, right? And so how can we sort of think about that? Well, it's not an exact apples to apples comparison, but if you think about a function like, say, fn of x is going to be, say, x squared divided by n, right? Now, if you fix any value of x, right? So if you fix x, then as n goes to infinity, fn of x goes to 0, right? So if you're taking just any specific value of x, then this will always tend towards 0. However, if you think about taking sort of the maximum difference between fn of x and 0, right? So that's the thing we're saying it's going to ultimately end up converging to. So if you take the supremum of this over x, right, and then you take the limit as n goes to infinity here, right? So what we're thinking about is we first take the maximum difference, and then we take the limit. This is going to be infinity, right? Because the issue is that as x sort of grows, we can't sort of keep pace with that over n. There's never going to be a time that if you take n big enough, it won't matter what x is. Whereas in this case, we are saying that even if you were to first find what's the maximum difference, and then you take n off to infinity, that's still going to go to 0. Right, so hopefully this sort of gives some intuition as to why this is a stronger result, but ultimately it is a stronger result. And so this sort of says that we have this uniform convergence. There's a lot more sort of additional theoretical results that you can take, and if you take sort of an advanced statistics course, you'll definitely deal with this a lot more there. But the general idea here is that the empirical CDF is going to be a good estimator. It's going to be a well-behaved estimator for the true CDF. And in particular, what we need is we need our sample size to be going off to infinity. And so just sort of as a follow-on to that point, we can pull back open the course notes here, and I'm running the exact same analysis that we saw above, except now I'm going to be considering 20, 200, and 20,000 data points, right? We can see we're generating exactly the same data before. And so these first plots are exactly the same as what we saw above. But then what you can see is that in this case where we're taking 200 data points, right, and we look at the normal curve right here, you could hardly even see a difference between the normal CDF and the empirical CDF that we have here, right? They're essentially one and the same. And we don't have the actual CDF plotted here, but you can see it's sort of converging to this line. If we go up to 20,000 points, now they are literally coinciding with one another. And so we can sort of trust that this one is also going to be coinciding here as well. So as the sample size increases, then we have this sort of position whereby the empirical CDF is going to be essentially a perfect representation of the true CDF, right? And so again, there's sort of these two framings for it. And we've been, jumping back and forth between them. But on one hand, the empirical CDF is a true CDF of a discrete distribution based on the data that we've actually observed. On the other hand, the empirical CDF is going to be a distribution an estimate of the true distribution function, right? And so either of those framings are going to be useful depending on exactly what it is that we're trying to do here. And so how does this all help us? Well, on one hand, this is just another example of a nonparametric estimator, right? The empirical CDF is a nonparametric estimator of the distribution function. However, the nonparametric estimator of the distribution function, the empirical CDF here, is also going to give us a way to generally form nonparametric estimators for any parameters that we care about, right? And so what we can think about here is if we want to estimate say theta of f, right? So again, we're sort of framing the parameter that we're looking to estimate as a functional over the distributions. This was the setup we were in last time. Then what we can do is we can use theta hat is equal to theta of f hat n. Right, and so what are we actually saying here? Well, we know that theta of f is just sort of saying this is going to be some functional from the CDFs to the real values, right? So every CDF gets mapped to some real value. We've said that this is just a CDF, right? The empirical CDF is just some CDF. And so we could apply that same functional to the empirical CDF. And in doing so, that's going to produce us a real value. And what we're saying is that that real value is going to be an estimate for the true parameter value, right? And so sort of what's the rationale here? Well, very informally, the idea is that if we take the limit as n goes to infinity of f hat of n, then what we're going to sort of get is that this is going to tend towards f, right? And so the idea is that, well, if we take the limit, if we take a function and we apply it to both sides, or a functional, right? So we do the limit as n goes to infinity of f hat of n, then that should sort of tend to be theta of f, right? And here, our hope is that if theta's sort of a well-behaved functional, then maybe this will be sort of valid to do, right? Where we can pull through the limit. Now, I will sort of point out that this step is not always going to be justified, right? We need theta to sort of be well-behaved, and there's going to be plenty of examples where you're sort of not justified in doing this. But that's the general theory, right? Is that we know this is true. And so if we know that's true, we can sort of hope to be able to work in this direction, right? And the really nice part about this is that this is going to give us sort of a non-parametric way of estimating any parameter that we can sort of frame as a functional here, right? And so, how can we do this? Well, like we were saying before, if you suppose that theta of f is going to be an integral of, say, g of x times df of x, right? So it's this integral over the function. Well, then this integral right here, if applied to f hat of n, right? So theta of f hat of n, we know is going to be this integral over the reals of g of x d f hat n of x. And what we've said is that this integral right here, because we're moving to the discrete case, the integral becomes a summation, and then we sort of have to sum up of the mass function multiplying by the function that we care about. And so our mass function is going to be 1 over n for all of the values that we've observed. So this is going to be equal to the sum from I equals 1 to n of, say, g xi times by 1 over n, which is 1 over n, the sum from I equals 1 to n of g of xi. Right, so any parameter that we can write out as the integral of some function is going to be sort of represented as the average, the sample average of this based on our data. And so why might this be useful? Well, for instance, if we wanted to estimate, say, the variance of x, right, then if we want to frame this as theta f, right, this is the integral of x minus the expected value of x squared df of x, right? And so the way that we can do this then is theta of f hat of n is going to be 1 over n, the sum from I equals 1 to n of xi minus x bar squared, right? And so immediately we sort of get this plug-in estimator for the parameter of interest. Now note, this is not the sample variance estimator, but it's going to be sort of an estimator that's going to be reasonable, that's going to work well. If you were to just take, say, the expected value of x, then this is just going to be the integral of x df of x, right? And so then theta of f hat of n is going to be 1 over n, the sum from I equals 1 to n of xi. And so then we get back to our sample mean here, right? And so this plug-in principle is going to become sort of a really, really effective way of generating these non-parametric estimators. And the idea is essentially that what we're wanting to do is we want theta of f, right? But we don't sort of know how we're going to go directly to sort of an estimate for that. So that what we say is that we can do sort of f here is going to be well estimated by f hat of n. And so then we can go, well, theta of f hat of n should hopefully give us sort of this theta hat that we need, right? And so it's not always going to work, but it's sort of this intriguing little idea here. And it's going to be this idea that requires a couple of leaps for us, right? So it's first to start thinking about parameters as functionals of the distributions. And the second thing that it's going to require is us to recognize that the empirical CDF is going to be a good estimator for this, right? And so just to sort of finish out the lecture today, we'll just sort of plug through this little piece of the notes here. Again, I would encourage you to actually sort of, read through these in a little bit more detail. But so what we're thinking about is, again, any functional that we want to specify here, right? So for instance, the expected value, then the idea is that we can take our estimator to be given by the plug-in estimator, or we plug in our empirical CDF into the functional, right? And so we can see here the expected value. We can see here the variance. One of the things that we'll do sometimes by way of notation is we'll write the expected value with the distribution sort of indicated here, right? So this is the expected value with respect to f. The reason that that's useful is that then when we want to plug in f hat of n, then you know that we need to take the expected value with respect to the distribution f hat of n, which is just going to be the sample mean here. As a general rule, we don't need to make very strong assumptions here. We'll need theta hat or theta to be a well-behaved functional in order for this to produce good estimates, but it's going to work well enough for us. And so that's sort of all that I'm going to talk about in terms of forming non-parametric estimators. When we come back from the break, we'll start talking about how we can use this to start doing sort of these non-parametric Monte Carlo techniques based on what we'll call the bootstrap, right? And so again, if you're interested, you can start to read ahead in the notes that this will be posted to the course website, and so you can sort of see that there. But just note that this is, a very, very small piece of what non-parametric statistics has to offer. If you want to get sort of more involved in any of this, it's going to require sort of a lot more studying, right? You could take a full course or multiple courses on these topics. And so it's okay if you sort of felt like this moved pretty quickly. My hope here is to mostly give you a flavor for what we're doing here, so that when we start to see the bootstrap, which I think will be a lot more understandable, you can sort of tie it back to what we talked about here. But again, that's everything sort of wanted to talk about today. I hope you all have a great break, and I will see you all afterwards. Please do not hesitate to reach out if you have any questions about anything. And yeah, I will see you all soon.